Okay, so here, now we're going to begin to actually construct the intervals. So the first thing we need to do is making sure all the preliminaries, right, part ones and part two are satisfied. So notice that it must come from a random sample, right? And we need the sample size to be no more than 5% of the population, right? So that was like part one, right? And then the sample size has to be greater than or equal to 30. That was also part one, right? And the other one is that we may not need this because it may just tell us that the population is normally distributed. So if it just tells us this, then we're part one is done and we just move on, right? If not, we will have to satisfy these. And then recall part two was the distribution, right? And then part one was these three bullets. Okay, so the formula for the confidence interval is right here. The lower bound is the sample mean minus the t-score, t-value from the student t-distribution times the standard error with respect to the sample. And notice it's the same exact expression, but adding for the upper bound. So again here, if I drew a line, okay, so here is the lower bound. Here's the upper bound, and somewhere inside is going to be mu, right? And then this is the MOE. So the lower bound is going to be the sample mean minus the MO, and then the sample mean plus the MO, and then we say, okay, the population mean lies somewhere within this range. So again, we're not going to use this formula, and if you want to, you can. However, it's not required, but I've seen some students like it because they are, they feel like they're filling in a formula. I encourage you to use the calculator, and I expect you to use the calculator, especially when it comes to quizzes and exams. So, why not? It's just so much quicker and more accurate. So it's right there in stat, and if we go to test, we'll go to t-interval. So let me show that. Here's stat, and go over to test, and if you see, there's like this huge list of tests. Well, I have to tell you, we are going to use all these tests eventually. So just go ahead and get comfortable with this menu because we're going to be using it quite a bit starting right now. So we're going to do a t-interval, which is number 8. And we could either input data from our lists, or if we're given stats, notice the menu changes and we just can enter some stats. So it works out. Okay, and we need to know a few things, right? Right, we need to know the confidence interval, right? And we need to know the statistics or data, whatever we need, and then we can hit enter. So it's pretty simple. So if we take that penny example and find 99% confidence interval in which the population mean weight of a penny will lie, we have to go back to that example. So if I went back to the penny example way up here, it was a simple random sample, but notice it didn't tell us anything about the population. I mean, we did get a point estimate for the population, but that's about it. So I think what we're going to have to do here is actually test for normality. But here we are given this raw data. And if I wanted to count how many pieces of data, notice that I have 17. So let me go ahead now and go back to that screen. Okay, and we'll have to do some preliminaries. So let me start over here with part 1. Part 1 says for a mean that my sample, which is equal to 17, can be no more than 5% of all pennies. Right? I think 17 pennies is way less than all the pennies out there in the world, right? So that one is for sure done. The second part is making sure that if it's not given to be normal, that the sample size is greater than or equal to 30. And notice that this one fails. Don't even go into the distribution, right? Like, just know that it fails at this point. So we're going to have to test for normality, right? So there is a way with raw data. Recall that back in the day when we wanted to test for normality or a bell curve, there were a few ways we could do that, right? It was a histogram, box plot, and yeah, I think those two are fine. We could just use those. So let's go ahead and put in the calculator those pennies. Well, I think we did already. Mine's still there in list 2. So let me go ahead and just plot a histogram or a box plot, right? So I'll do a box plot just because I like box plots. I think they're so useful. So hit on. Again, I went to second stat plot. Recall how to do that. And then I'm going to do a box plot and see if there's any outliers. My values are in list 2. I leave frequency as 1, and then I'll mark blue. And then I'll go to zoom stat, right? Number 9, zoom 9. And so here, the box plot is nice because if the box plot shows no outliers, then we can assume normality. We can assume the data comes from a normal population. So I think that the box plot is the best way to go in this case because do the box plot with the outlier, and if there's none, then we can just assume that the sample comes from a normal population. Okay, so once part 1 and part 2 are done, part 1 is done, then we can go ahead and say, okay, because we have determined now that the data has come from a normal approximately a normal population, we can go ahead and calculate the confidence interval. So let's go ahead and do that. Okay, and we were looking at 99%. So what you want to do is go into the calculator and go to T interval, and go ahead and enter a data, right? Everything is in data. We're not going to put in the distribution because we have raw data, so you always pick data and just pick the list that your data is in. Okay, so let me go back. Again, do you remember? Go to stat, go to test, go to T interval, and select data. Why are we selecting data? Because our data was raw and we put our data in a list. And under list, put where the data is inputted. Now mine is in list 2. Remember, because I don't know why. I didn't have a frequency column. Notice the confidence level defaults to 95. Ours is 99. And you're going to put 0.99, the actual decimal, because we can't do arithmetic operations with percentages, remember? Okay. So now here hit calculate. And notice that it gives us this T interval. And let me drag this over. So here is what the calculator gives us. It gives us a parenthesis 2.4516, comma 2.4767. So that is the numerical values, like that's the math part. But what I want us to do is have a conversation about this. Let's talk about it. What does this mean? Well, let's not forget. So we are 99% confident that the population mean weight of pennies lies within 2.4516 and 2.4767 grams. So it's really important you learn how to interpret, and I would practice this interpretation because there's a future project where I want you to interpret, and then in probably the future quiz, probably an interpretation. All right, let's move on from pennies. That's not the last time you'll see pennies, though, in our notes. So the effectiveness of a blood pressure drug is being investigated. An experimenter finds that on average, the reduction in symbolic pressure is 22.1 millimeters of mercury for a sample size of 788 with a standard deviation of 20.8 millimeters of mercury. How much millimeters of mercury will lower for a typical patient's systolic blood pressure after taking the drug? Estimate with 90% confidence. So notice once again, they did not tell us anything about the population, but I do know that I want to note some things. So they did say that the average is this and the standard deviation is this. So that's your red flag that this is going to be a mean. The other part we want to highlight is that they're saying 90% confidence. They don't specifically ask for a confidence interval, but knowing 90% confidence, we're going to go ahead and find the confidence interval at 90%. Okay, and so they did not tell us it was normal, so we're going to have to do part 1. And I usually like to do it like somewhere in the margin. So the first part is we want to make sure the sample size of 788 is less than or no more than 5% of all what? Right, patients, right? With blood pressure, right? Well, 788 people is way less than 5% because everybody has a blood pressure, right? So this one's done. The second part is our sample size, does our sample come from a approximately normal distribution, right? Well, if it's 788, this has to be greater than or equal to 30, and it is. So we can go ahead and assume the population in which the sample came from was normal. Okay, then I draw a line. Once that part 1 suffices, now we can go ahead and continue with the problem. Okay, you have to do part 1. Unless it says the population is normal, then we can go directly to the problem. But here we have to test these preliminaries. So now we can go to the confidence interval. And we're going to do it at 90%. So notice that here we don't have raw data, so they're giving us the statistics. So we're going to select stats on our T interval. And then we do know that the average for the sample is 22.1. And the sample standard deviation is 20.8, and the sample size is 788. So let's go to the calculator. Okay, do you remember where it is? Stat, test, T interval, number 8. So we do not have a list or raw data, so go directly to stats, hit enter. The new menu will come up, and we'll clear this out, and we'll put the new sample mean, 22.1. The sample standard deviation, which is 20.8. And the sample size is 788. Recall that the confidence level we wanted was 90%, so make sure you change that to 0.90. And then go ahead and hit calculate. So this gives us 20.88 to 23.32. So let's not forget what this means. So if I wanted to draw it, I just want to kind of have you recall what this means. Right? So here's x bar, and when I subtract the margin of error and add the margin of error, I get these lower bounds, right? The 20.88 and 23.32. So this means that the population average of systolic blood pressure is between the lower bound and this upper bound. So let's go ahead and interpret this. This says that we are 90% confident that a patient's systolic blood pressure, SBP, right, will lower somewhere between 20.88 and 23.32 millimeters of mercury, right? mmHg. And so they're just saying, like, if the patients take this drug that have high blood pressure, we are 90% confident that the patient's blood pressure will lower by 20.88 and 23.32 millimeters of mercury.